All right, in the second video, what we're going to be doing is taking information about graphs and functions and the derivatives and actually putting them as a graph and see if we can transition it to what it looks like. In this first problem, we are looking at a function who the function value when x is -1 is 0. So we're just going to start right there. We're just going to start with a graph and just kind of introduce things one at a time, all right? And actually, it might be beneficial to actually have some of this. All right, so sorry that the text is not quite lined up. I didn't realize I needed these graph papers. All right, so the function value when x is -1 is 0. So that's where you start, right there. We've already included the first piece of information. Now, what's the next piece of information? The derivative is negative to the left of this point. So to the left of this point, we need to be going down. So like somewhere, maybe in a different color or something, but to the left, we should be going down. But actually, that's up. Be very careful, right? From the left, we should be going down to approach this point. All right, it's decreasing here. Another thing that you can write is just write decreasing over here, DEC. Next piece of information, this third one, the derivative at this specific point is also 0. So remember, that means relative maximum or relative minimum. It means horizontal tangent line. So very locally, we have kind of like this flat line at the function. And then to the right of this point, our derivative is positive. So to the right, we should be increasing. So as we come in from the left, we should be decreasing. As we hit this point, we should be about flat. As we go to the right, we should be increasing. So maybe it looks something like this. Decreasing, kind of flat, increasing. That could work. Once you give your graph, double check, go through all of these things again and see that we're satisfying everything. So is the function value when x is -1 equal to 0? Yep, we have that point right there. Are we going downwards to the left of this point? Yep. This is all going down. Are we going upwards to the right of the point? Yep. And are we flat at the point? Yeah, we're kind of flat around there. Sure. So add each information one at a time. Draw your graph. Then go back into the information and verify that you have indeed done it correctly. And that's the first one. So the second one has a lot more things, a lot more going on, and we're going to start talking about the second derivative in part B here. So it's only defined for positive numbers. So on the next page where we start incorporating the information, let's only define it for positive numbers. And again, let's have some actual graphs. Whoa, not that one. All right, so here's going to be what we have. So we don't have to worry about quadrants 2 and 3. Only defined for positive numbers. Good, we're on the right start. Next piece of information. The point 0, 0 and 5, 6 are on the graph. So we're just going to go plot them. 0, 0 is right here. 5, 6, 1, 2, 3, 4, 5. This is 5. 1, 2, 3, 4, 5. This is 5. All right, let's see if I can do this. No, I can't. I tried. Oh, whoa! How about that? All right. All right, so the point 5, 6 is also on the graph. X is 5, Y is 6. All right, we've incorporated the first two pieces of information. What's the third information? Right here. The derivative is positive from 0 to infinity. And remember, 0 to infinity, that's our whole domain. So we're increasing. Positive derivative means increasing on our whole domain. All right, so everywhere we're increasing. So make a note. increasing everywhere. So again, we don't know much about the second derivative. So, you know, maybe it's going to go up like this, or maybe it's going to go up like this, or up like this. All we know is that it's going to be increasing everywhere. It's only going up. Next piece of information. It's concave down, negative second derivative, concave down from 0 to 5. All right, so maybe in this interval, it's concave down, so maybe it looks kind of like this. Who knows? Actually, can't look like this, right? Because this is increasing for the beginning and then decreasing for the end. So it's concave down, but it's still increasing. So maybe kind of like this. It's increasing, but it's still got that kind of downwards parabola shape. The second derivative at 5 is 0. Second derivative right here is 0. Let's sit on that piece of information for a little bit. And finally, the second derivative is positive to the right of the second point. So it's going to be concave up after this point. And again, it's only increasing. So it's got to be concave down in the first region, concave up in the second region, and it's got to be increasing everywhere, which makes this right here a point of inflection because it changes concavity. So maybe it looks kind of a little something like this. Kind of a little hard to see. Move it a little bit over like this. Maybe it just keeps on curving up. Like so. And we'll pretend that these are connected. All right, so that's my guess. Now let's go back through and verify that we've done everything right. So it's only defined for x greater than or equal to 0. Yep, our function is only defined for x greater than or equal to 0. There's nothing over here. All right, what's next? Are 0, 0, and 5, 6 on the graph? 0, 0 is right there. 5, 6 is right there. Good. Is the derivative positive? Is it increasing everywhere? Yep, it's increasing everywhere. It gets a little close to flat here, but it never actually gets flat. All right. Are we concave down from 0 to 5? Yep, concave down right here. Sure. Are we concave up from 5 to infinity? It's kind of hard to see. Let's maybe clean it up a little bit. Make it a little easier to see this point of inflection. Like this. All right, now it's very obviously concave up in this region. Good. And then we have a point of inflection right here because it changes concavity. So good, we're good to go. And if you want to keep this stuff down here, that's fine. You don't need to erase it. I'm okay with that. Let's do one more problem to show this off. So this one only looks at 3. All right. We have a function, and I'm just curious about the function value, the derivative, and the second derivative when x is 3. And what does it look like locally around there? All right. So we set up our graph. We only care about when x is 3. So again, we don't really care about negative numbers in the x coordinate. F of 3 is equal to negative 2. So we're going to start by drawing that. Good. F prime of 3 is 0. Remember, f prime, that's the derivative. The derivative of 0 means that very locally, it's flat. If it were a positive number, it would look like this locally. If it were a negative, it would look like this locally, going down. But locally, it's kind of flat. The first derivative is 0. The second derivative is 1. Second derivative is positive, right? Which means it kind of looks like an upwards parabola. And again, it has to kind of flatten out right there. So maybe it looks like this. We don't really know a lot about this function, only around this point. All right. So that's just what part C is asking for. All right, and that's that's that. If I can pause the video. Good luck.